Good night, and yours truly, Dolphy Gilpin. It's coming to you from 1524 LaVista Drive, Decatur, Georgia, United States of America. I'm on the second floor, and I'm also on the amazing 5 cos 12 matrix, and its derivative now. Matrices. That's the topic, amazing 5 cos 12 matrix and its derivative matrices. That is the breakdown from the 5 cos 12 into 4 by 4, 3 by 3, and 2 by 2s during the PDM or partial derivative process. And specifically tonight, we are on now the application of this 5 cos 12 matrix and its derivative in closed confined spaces. Here am I in the closet on the second floor. At 1524 LaVista Drive, the closet. And this is analogous now to pilot. They have to work in their cockpit and in their cabins, in closed spaces, whereas the body of the airplane carry the passengers, and they are in these confined spaces, doing their maneuvering of the aircraft. Also, rockets, astronauts have to be in confined spaces working, and this is analogous to such a situation. I have done some of these lectures in other places, as in Brooklyn, New York, on aircraft modeling, and so tonight I'm going to be skipping out a lot of the steps, and assume now that my audience are advanced and are up to date with some of the parameters and terms being used here. So we're going to be doing now the rotation matrix, which was done in Brooklyn, New York, for wind and stability axis. And as we had mentioned then, that we had stumbled upon some of these 3 cos 3 in the wind and stability axis by the magnetization process of the AMZ5 cos 12 matrix. Yeah, the magnetization process. So we're going straight into it now, leaving out a lot of steps because the lectures have been done already. So what we have now, we are getting now the P wind, and by definition we had also know that what the P, Q, and R stand for, and the U, V, and W, those are also defined in previous lectures. So P wind is now equal to this 3 cos 3 cos beta sine beta and 0 minus sine beta cos beta zero and 0 0 1. So here we have this 3 cos 3 matrix, P wind, and this is now multiplied by P stability, STAB. All right, so we continue now that P stability was now equal to cosine alpha 0 minus sine alpha 0, 1, 0 sine alpha 0 cosine alpha. So know that the rotation matrix now become P wing equal now to cosine beta minus sine beta 0 sine beta cosine beta 0, 0, 0, 1. This is time now. Cosine alpha 0 minus sine alpha. These are now the elements of the 3 by 3 matrix. Minus sine alpha 0, 1, 0 sine alpha 0 cosine alpha. So we have now P wind is equal to that. And this is our now time P body. So of P wind is equal to this 3 cos 3 times P stability. And P stability is equal to this matrix times P body. And that now P wind, if we make the substitution now, is equal to this, which is this matrix here, times this matrix times P body. So that's what we get to there now. And so if we simplify this, these matrices operation, what we have is that P wind is now equal to, if I write the P wind down here, P wind is equal now to cosine alpha cosine beta. That's when we multiply these two matrices together. Now we get cosine alpha rows times column this element now would be minus cos alpha sine beta and minus sine alpha this would be now sine beta cosine beta 0 and now sine alpha cos beta minus sine alpha sine beta and cosine alpha. And this will be now time P body, which is the same P body here, times P body. So we multiply these two matrices now and we get cosine alpha, sine beta as the first row. And in the second row we have minus cos alpha, sine beta, cos beta, sine alpha, sine beta. And in the third we have minus sine alpha, 0, and cos alpha times P body. And this gives the following relationship between the velocity in body and wind axis. And so we get this relation now in body and wind axis. So what we have now is that V body will be equal now to U, V, and W. And we recall that U is the longitudinal velocity, V is the lateral velocity, and W is the vertical velocity. And if we simplify here, we'll have know that this is equal to making some oversimplification here, leaving out some steps. V resultant of V total times cosine alpha cosine beta. And V total here resultant times sine beta. And V sub t sine alpha cosine beta. So that's what we have for the V body with respect to U, V, and W, longitudinal velocity, lateral velocity, and vertical velocity. And so consequently now, we now have that U, which is the longitudinal velocity, would be equal now to Vt cosine alpha cosine beta. And that V, which is the lateral velocity, will now equal now to V sub t, which is the total velocity, sine beta. And W, which is the vertical velocity now, we call now V sub t sine alpha cosine beta. And so there we have it. Longitudinal velocity, the vertical velocity, and the lateral velocity and the vertical velocity. We'll call that V of t. V of t will be equal now to the square root of u squared plus v squared plus w squared, where u was the longitudinal velocity, v was the lateral velocity, and w was the vertical velocity. That's from the defined equation from the very first. And if you should define out of what the alpha is, though, that alpha was the angle of attack, alpha equals angle of attack and beta is equal to the side slip angle and we have now that tan alpha is equal to double over u, which is the vertical velocity over the longitudinal velocity, and that now sine beta is equal to v over vt. And we have the VFT is equal to square root now of u squared plus v squared plus w squared. And VFT as now the total speed. Yeah, so once again, here we have now the amazing 5x12 matrix and its derivatives now, breakdown matrices. And we could get to these breakdown matrices from the AMZ5X12 breakdown by equating coefficient. But we came across these equations by the magnetization properties of the AMZ5X12 matrix and their characteristic breakdown derivative matrices. So we'll continue with this topic on aircraft modeling and body fixed coordinate system for the aircraft. And we are applying this now in confined spaces. And specifically, we are here in Decatur, Georgia, in the closet on the second floor, applying the AMZ5X12 matrix in closet space, closed confined space. And we compare this now to pilots and astronauts working in confined spaces. So we'll continue with this AMZ5X12 matrix being applied in confined spaces. Let's take a break and we'll return. Now we return to our 1524 LaVista Drive, second floor, and we are on the application of the amazing 5x12 matrix and its derivatives now, the derivative matrices, to or in confined spaces. And in particular here, we are in the closet on the second floor at 1524 LaVista Drive, Decatur, Georgia. And this is now analogous to, as we have put it now, pilots and astronauts working in confined spaces, even in more compressed, if you should use the word, spaces. But this is just an analogy or comparison. And we have now define some of the terms that we were using. P as the roll weight. When we said P wing, the roll weight with respect to the wing, and Q as the pitch rate, R as the yaw rate, XC as the earth fix X position, Y sub E as the earth fix Y position, Z sub E, comma H as the earth fix Z position, axis downward, and altitude. You know, H represents altitude. Omega here is a roll angle, this Taylor is a pitch angle, and phi as the yaw angle. X, the longitudinal force, Y, the transverse force, Z, the vertical force, L, the roll moment, M, the pitch moment, and N equals the yaw moment. So as we review now, we said now that P wing, which is P was the roll weight, was equal now to cos beta in this 3x3 matrix. The first, the 1 element will be cos beta, the 1 2 element sine beta, and the 1 3 element will be 0. Or the 2 1 element minus sine beta, the 2 2 element cos beta, and the 2 3 element 0. The 3 1 element here 0, the 3 2 element 0, and the 3 3 element 0. So that P wing was equal to this 3x3 matrices times P stability. Now, P stability, which is the roll weight stability now, was equal now to this 3 cos 3 matrices times P body. And these are the elements of the 3 cos 3. Cos alpha, 0, sin alpha, 0, 1, 0, sin alpha, 0, cos alpha. And The rotation matrix now become P wind, which is the same P wind, which is equal to now to this 3 cross 3 times P stability. We substitute P stability now, this matrices, into the equation here, and we get now P wind is equal to this 3 cross 3 times this 3 cross 3 times P body. Simple amount of substitution. And then we multiply this matrices by this matrices and time P body, and so we get now cos alpha cos beta minus cos alpha sin beta minus sin alpha as a 1, 1, 2, 1, and 3, 1 elements, and sin beta cos beta 0 as a 1, 2, 2, 2, and 3, 2 elements, and sin alpha cos beta minus sin alpha sin beta and cos alpha as a 1, 3, 2, 3, and 3, 3 elements in the matrix. This is after the multiplication times P body. And subsequently we get now that V body is equal to U, V, and W, which is the longitudinal, transverse, and vertical velocity, and is equal now to V sub T, which is the total velocity times cos alpha cos beta. V sub T equals sin alpha sin beta, and V sub T sin alpha cos beta. And consequently, know that the U, or the longitudinal velocity, is equal to the total velocity cos alpha cos beta, and V is equal to the transverse velocity, the total velocity times sin beta, and the vertical velocity equal to the total velocity times sin alpha cos beta. And we have defined the term U, V, and W, and the V of T, which is equal to the square root of U squared plus V squared plus W squared. Alpha equal to the angle of attack, beta equal to the side slip angle, where tan alpha is equal to the vertical velocity over the longitudinal velocity, and sin beta, the side slip angle, is equal to V over V total. So that is a quick review of AMZ5X12M matrix and derivative matrices being applied in confined spaces, and specifically we're applying this maneuver in the closet and the second floor, 1524 LaVista, Decatur, Georgia, United States of America. So we'll now return to some other calculations here in our closet on the application of the amazing 5X12 matrix and its breakdown derivative matrices. Here's truly Dolphy Gilpin taking a break here, and we'll return with some further calculations.